Welcome to our video module on quantum mechanics. In this series, we're going to be exploring the ideas of upper-level quantum mechanics, following the basic structure of the Griffiths text. If you haven't had a chance to look at the history of the dawn of quantum mechanics in my previous two videos, I'd encourage you to check them out now because they're really interesting. Today, we're going to jump into the actual content by starting with a brief review of some of the physical phenomena that clearly represent quantum mechanic behavior. From there, we'll do a quick review of the equations we need to start exploring wave behavior. The first phenomenon is a double-slit experiment using light, which was first done in the early 1800s by Young. In this case, a light source sends photons in this direction. A small slit at A creates a point from which the light radiates. And in this case, the lines indicate peaks in the wave, and in between you can imagine troughs. The second wall here are two slits, B and C. And these create points of radiance at B and C that as they hit F combine either constructively, where we see the white light, or destructively, where we see these gaps in intensity. The interesting takeaway here is that we don't get to see the waves themselves. Rather, all we see is the light intensity, and if we decide to measure, we see that it's proportional to the magnitude of the electric field squared. The next phenomena is blackbody radiation. In this situation, we take some sort of material, change its temperature, and we find that as we change its temperature, it begins to emit electromagnetic radiation with certain characteristics. And classical theory predicted that the radiation intensity would be inversely proportional to the fourth power of the wavelength. This became an issue with small wavelengths where the radiation intensity would go to infinity. And it's the model where Planck found that it could be explained if the radiation was understood in terms of discrete quanta, with an energy relating to its frequency based on Planck's constant. The next concept is the photoelectric effect, where in gray we have some sort of substrate. When electromagnetic radiation is incident on this substrate, we see electrons radiated from it. By looking at the wavelength and energy of the photons and the electrons, interesting phenomenon surface where it isn't higher intensity photons that increase the energy of the electrons, but rather smaller wavelengths. The next item we'll look at is the interesting characteristics of emission and absorption radiation of hydrogen. We see it's not continuous, but in discrete energies. This establishes an inverse relationship between the wavelength and the Rydberg number divided by the final orbital number squared minus the initial orbital number squared, where the change in energy between the orbitals equals Planck's constant times F. The next phenomenon is Compton scattering. In this case, in gray, we have the initial condition of a photon coming up on an electron. After the collision, the photon has a new scattered angle, and the electron recoils at a certain theta. From this, we can identify a relationship between the momentum and the wavelength. Finally, the Stern-Gerlach apparatus allows us to fire an electron through some sort of non-uniform B field, and as a result, we see the electron change its trajectory from going straight to going up or down, and we can measure its location of where it hits this wall to identify properties of the electron. Each of these phenomena has demonstrated different aspects of wave behavior that are worth noting. Probably the biggest one is the relationship between energy and frequency. Another way to do that is to put in the corrected Planck's constant with frequency as radians per second in the form of omega. With Compton scattering, we have a relationship between the momentum and the wavelength. And there's also basic equations that describe waves. So the frequency is equal to the velocity over the wavelength, or if we're dealing with electromagnetic radiation, it's simply c over the wavelength. And a friendly reminder that the frequency is inversely proportional to the period. We also model wave behavior with the equation psi equals e to the I kx minus omega t, where k is a sort of stretch factor relating to the wavelength of 2 pi over the wavelength. So in summary, these 6 physical phenomena provide a starting point for us to explore quantum behavior in nature, and I've reviewed the big takeaway relationships or equations in cyan here for your convenience that, quite frankly, are worth your time to memorize. Thanks for your time, and I look forward to catching up with you in our next video as we explore this further.